Welcome to Math Minders Academy. If this is your first time joining our channel and you are yet to subscribe, go now, smash the subscribe button, hit the notification bell icon so that each time we produce a new video, you'll be among the first to receive it. Like, share this video, go to the comment section and share your views. Guys, please help us subscribe this video. If you value the work we are doing, one of the ways you can help us to reach out to the vast majority of students is to subscribe so that the YouTube algorithm will take this video around to reach as many students as possible. That is our mission. We want to see how possible we can make mathematics interesting and simplify it as much as possible. So help us. If you have not subscribed, encourage your friends to subscribe. Let's go. So today, guys, we are going to look at volume of compound shape. So many compound shapes. What we are going to do in today's tutorial class will help us to understand how to handle any compound shape. The one we are going to do today, which will be an example and which will set the pace for very many other compound shapes, is a hemisphere surmounted by a cone. Sometimes it might even be given a cube surmounted by a pyramid. The same principle works. So we are going to break it down in a way that by extension, we can apply the principle to any other compound shape. So what you see on your screen is a compound shape. It's a compound shape because it's a combination of a hemisphere and a cone. All right, so what is the first step in handling this compound shape? We're going to look at the first thing we need to bear in mind. Of course, this is the compound shape given to us. We're going to look at a hypothetical question that will help us to navigate through, the steps required to get the volume of this compound shape. So let's look at this together. If we are told that a solid consists of a cone attached to a hemisphere, calculate the volume of the solid if the diameter of the hemisphere is 3 centimeters and the overall height of the object is 7 centimeters. Leave your answer to 1 decimal place. So this is the question. Now, this question is going to help us to explore all the possibilities, explain all the required steps needed in order for us to get the volume of this compound shape so that we can still apply this knowledge to solving other compound shapes. Let's go. So the first is to look at the height. We are told that the height of this solid is 7 centimeters. So we put the height where it's meant to be. Now we are also told something about the diameter of the hemisphere. The diameter is 3 centimeters. Of course, you understand that, if diameter is a given number, radius is actually half of diameter. So, and diameter is from one part of the circumference to another passing through the center. The line that touches the circumference, 2 points on the circumference of a circle, and it passes through the center. If you look at the hemisphere, it has a circular top. So we'll get the diameter. Again, the diameter can still be vertical, right? From the center of the hemisphere, down to the bottom. That's also radius. The diameter is the entire line that touches the both sides of the circumference. So we can still take it down from center to the bottom to get the radius. And the radius is actually half of the diameter. And that's how we got 1.5. Now, the next step is to break this compound shape into their simpler parts. So The compound shape, we break it into hemisphere and cone. So we can see the two solid shapes that we are joined together to make this compound shape. So we're able to detach them. So here, we look at the cone and we figure out what the height of the cone is. If the height of the entire solid is 7 centimeters, then the height of the cone is going to be the height of the solid minus the radius of the hemisphere. That is 7 centimeters minus 1.5 centimeters. And that gives us 5.5 centimeters. That is actually the height of the cone. Okay, we've now been able to sort out the height of the cone. So with this information, we can move on now to the solution to calculate the volume of this compound shape. So how do we get it? It's going to be the volume of the hemisphere plus the volume of the cone. So we said the volume of the solid equals the volume of hemisphere plus the volume of cone. And now the volume of this solid will give us the combination of the volume of hemisphere and cone. For hemisphere, the volume is 2/3 pi r cube. And for cone, the volume is 1/3 pi r squared h. Of course, how did we get the volume of hemisphere? We divide the volume of sphere by 2. The volume of a sphere is 4/3 pi r cube. So if we divide that by 2, it gives us the volume of a hemisphere. And that's what we use in this formula. So we go on now to put in all the items that we have sorted out, like the radius. We say that the radius is 1.5, which also serves as the radius of the cone, because both the cone and the hemisphere are connected by one circular part. The circular top of the hemisphere is the same as the base of the cone. So they have the same radius, 1.5. And that is why for the volume of hemisphere, we are using 2/3 pi times 1.5 cube. And for that of cone, we use 1/3 times pi times 1.5 squared, then times the height of the cone is 5.5. But remember here that we still retain our pi and want to evaluate pi at the end of this calculation. The reason is for us to avoid unnecessary approximation that might affect the final result. So we keep the solution well balanced by still maintaining pi until we get to the last stage of the calculation. We'll now evaluate the, we put in the value of pi and then get our final result. So here we multiply out. When we multiply out, 2/3 pi times 1.5 cube, it gives us 9/4 pi. And when we multiply 1/3 times pi times 1/5 squared times 5.5, it gives us 33/6 pi. Then these two values added together will give us 6.375 pi. All right, cubic centimeter. Remember, that's volume. So we move on now to, put in the value of pi, which here is 22/7. Of course, also note that if you are told to use 3.142, you make use of that. But since there's no specific instruction as regard the use of 3.142, we stick to the use of 22/7, which is more general to the approximate value of pi. And so when we multiply 6.375 by 22/7, it gives us 20.0357 and some other numbers that keep recurring. So now the volume finally of this compound shape is approximately 20.0 cubic centimeters to 1 decimal place. Let's proceed to the next problem. This one deals with volume and density of disk. Let's consider an example of how to handle this kind of problem. So guys, this disk is arranged in a way that one is on top of another. But there's something I want us to understand here. If you look at this disk, you will see that it is perfectly closed. If you turn it over, if you turn it over, you will see that there is no indication of a hole drilled anywhere. Now, that is the base. Let's go to the top, right? It's perfectly closed. But the question tells us that a hole 2 centimeters in diameter is drilled out. So when this hole is drilled out, how will this pattern look like? So now we are going to drill out this hole, and we will see what will come out of this process. So when we drill out this hole from this formally arranged cylindrical object, we now obtain disk. Now you will discover here that a hole is now created across these 3 cylindrical objects. Look at it. You can see it, guys. You can see the hole. Let's turn to the back. You can see. You can see the hole 2 centimeters in diameter. You can see the hole 2 centimeters in diameter. So the challenge now, guys, is how can we determine the volume of this object? So we need to get the volume of this object before we go ahead to calculate the mass. All right? So we are going to proceed now to see the steps required in order for us to perfectly calculate the volume of this open disk. Let's go. So guys, we are going to now consider a question that will help us to properly explain how to find the volume of this casting. So let's see the question. So now, if we are told that a solid aluminum casting for a pulley consists of 3 discs, and we can see the disc, in the given diagram, each 1.5 centimeter disc thick of diameters 4 centimeters, 6 centimeters, and 8 centimeters. A central hole 2 centimeters in diameter is drilled out, as in the diagram, if the density of aluminum is 2.8 grams per cubic centimeter. Calculate the mass of the casting. So guys, you can see the diagram is already depicting the information given to us in the problem. Okay, we've seen the hole created when this part of the casting is dug out. The hole that is formed is in the pattern of a cylinder. All right, that hole is cylindrical, and that is why the second diagram is showing us a cylinder. It's like a cylinder is pulled, a cylinder with a height longer than the height of each of the discs is pulled out, to create that hole. So we are going to see how can we put all these pieces together and then use them to find the volume of this casting and also proceed to find the density of this casting. Now, the entire arrangement of these 3 discs from top to bottom is 4.5 centimeters in height. How did we get that? Each disc is 1.5 centimeters thick. That's the thickness. And then when we assemble them, like that in 3 places, we get 1.5, 1.5, 1.5, and that gives us 4.5. And that's also going to be the height of that cylindrical material that is dug out, or the cylindrical pattern that is created when a hole is dug. So we now proceed to look at the solution. Remember also that we are given the diameter of each of the discs. The first disc, the topmost one, all right, out of the 3 discs, the top one, we are told that the diameter is 4 centimeters. We use arrow 1 to represent the radius, and it's going to be 2 centimeters. That is diameter over 2, 4 centimeters over 2. That gives us 2 centimeters. The middle disc has diameter 6 centimeters. So the radius is arrow 2, which gives us 3 centimeters. That is diameter over 2. We also do the same thing, 6 centimeters over 2. That gives us 3 centimeters. The base disc is of diameter 8 centimeters. And so the radius is arrow 3, which is half of the diameter, and that gives us 4 centimeters. But what of the pattern that is created, which is also in the form of a cylinder? That hole has diameter 2 centimeters. So the radius is going to be 1 centimeter. So with this information, we can proceed to look at the volume of casting. That will be the volume of the top cylinder. Out of the 3 cylinders, the top, that would be pi times 2 squared times 1.5. Remember also that the volume of a cylinder is pi arrow squared h, right? Where the h is the height. So here, for the first cylinder, the smaller out of these 3, the volume is pi times 2 squared times 1.5. The middle cylinder, the volume is pi times 3 squared times 1.5. And the base cylinder, which is the biggest of the 3, the volume is pi times 4 squared times 1.5. Then because a cylindrical pattern, is created, so we are going to subtract. It's like that cylinder is dug out. That's why I'm showing a cylinder, a kind of a cylinder with a smaller diameter, but a height longer, than the height of each of these discs. So it's a pattern that is created in form of a cylinder. So we subtract the volume of that out. That gives us pi times 1 squared times 4.5. All this together will give us 6 pi plus 13.5 pi plus 24 pi minus 4.5 pi. Altogether, it gives us 39 pi cubic centimeters. Bear in mind that in this calculation, we still retain pi until we get to the end before we factor in the value of pi. The reason is for us to be able to overcome, challenges that students often face when they are managing their level of accuracies. So when you are bringing in pi in the middle of your calculation, it can actually alter the accuracy, level of whatever you are doing. So we still hold on to that pi until we are able to finish this calculation. So we proceed now to see how to get the mass. So we've seen the volume, 39 pi cubic centimeter. Here, mass is density times volume. And we are told here that the density is 2.8 grams per cubic centimeter. What does it mean? That for every 1 cubic centimeter, the mass is 2.8 grams. And so when we have 39 pi cubic centimeter, the mass is going to be 2.8 grams, times that 39 pi cubic centimeter. So that's why we are multiplying density and volume to get the entire mass of this casting. And that gives us 2.8 times 39 times 22/7, which is the value of pi. Sometimes you might be given the value of pi as 3.142, but because it's not specifically mentioned in the question, so we use a more general value, which is 22/7. And that simplifies to 343.2 grams. Guys, that is the mass of this entire casting. We can proceed to change this mass. Of course, the final answer in grams is good, but again, we can decide to move it to kilogram. If you are asked to change it to kilogram, what do? You divide by 1,000. And when you divide by 1,000, it gives you 0.343. Of course, it's 0.3432 kilograms, depending on the level of accuracy required. If we are told to write this to 3 significant figure or write to 3 decimal places, is going to be 0.343 kilograms. Guys, that will be the mass of this solid aluminum casting. All other problems related to this follows the same process. Guys, did you find value in today's video? If you do, and you are yet to subscribe to our channel, we urge you to help us to make these videos go viral. We want it to reach as many students as possible, so that those that are struggling with some concepts, we try to animate some of these concepts to make them appealing to students. So we urge you, please subscribe, share this video, like it, so that the YouTube algorithm can speed it up and circulate it around so that other learners can have access to this video. Go to the comment section. Tell us what you feel about this video. Do you have area of mathematics that you are struggling with and you want us to animate it and discuss it together? Tell us in the comment section. We will not hesitate to build a video on that. We look forward to seeing you again in another tutorial class. This is Maths Minders Academy saying goodbye for now.
In the midnight glow where the stars align, we lose ourselves in the rhythm divine. Underneath the sky painted with dreams, we're chasing the echoes of silent screams. Caught